The last video of this chapter is video 9, and we're going to do a couple of extra challenge problems. Now, you didn't get any notes for these in class, so I encourage you to try these on your own. Pause the video, try them out on your own, and then kind of fast forward the video, see if you got the same answer as I did. If not, then go back and re-watch how I'm really doing these problems. So to the first problem. It says if the volume of a sphere is the same as the surface area of the same sphere, then what must its radius be equal to? So if you want, you could pause, try to work this problem out, see what you can do. If not, then here's what we're going to do. So we know we're dealing with two things here, the volume of a sphere and the surface area of the same sphere. Therefore, they have the same radius. So we want the volume to equal the surface area. So let me just write out, well, what are the two formulas for volume and surface area of a sphere? Well, volume is 4/3 pi r cubed, and surface area is 4 pi r squared. Now, since I was told that I have the same sphere, again, I can assume that this radius and this radius are the same radius. So now I need to solve for r. And at first glance, you might look at this and go, man, we've got a cubed over here and a squared over here. This is going to be some sort of crazy factoring problem. But it's not, because we don't really have any addition subtraction stuff going on with constants as well. So here's how we're going to tackle this. The first thing I immediately notice is that both sides have a pi. So if I divide both sides by pi, they both go away. Nice. So let's get rid of our pi factors. Oh, a little bit bigger there. There we go. So pi's are gone. Now, maybe I start working on my numerical terms here, my coefficients. I got 4/3 really now times r cubed equals 4 times r squared. Let's say I want to get the r cubed all by itself. Okay, so let's divide the 4 over. And since I have a fraction over here, I'm going to do something slightly different. I'm going to multiply both sides by a 4th. Okay, because 1/4 of 4 makes 1, and it's the same thing as taking 4 divided by 4. Now over here, these 4's can cancel out top and bottom, and I'm left with now 1/3 r cubed equals r squared. Now, what can I really do here? Well, I could divide both sides by r squared. You might think of, well, why don't I subtract it over? I could subtract it over, but I could also divide it over, because r squared divided by r squared ends up being, it's not 0 anymore, right? It's 1. And r cubed divided by r squared, well, 2 of my cubes here will cancel out, and that'll leave me with just r. So I end up having 1/3 times the radius equals 1. And now, maybe this is where I should have maybe thrown the 4/3 over instead of the 4 over to the other side. I'm going to multiply both sides by 3, and I get that the radius is 3. So if I just wanted to double check real quick, is it true that 4/3 pi r cubed is really equal to 4 pi r squared when r is 3? So I put 3 into there, and I'm going to put 3 into here. Well, let's see here. You can kind of look and compare. They're pretty much the same, right? And one thing I notice here is in the 4/3, I really have 3 to the first power, and here I have 3 to the third power. Well, this 3 to the first power that's in the denominator can knock out with one of my cubes and leave me with a squared left over. So essentially, I'll have 4 pi 3 squared, which is equal to 4 pi 3 squared. So I will end up with the same thing. I mean, you could plug all of this into your calculator and all of this into your calculator, and you'll end up with the same decimal numbers in both cases. The next problem, again, you can pause, you can kind of look at this, try to work it out on your own, or here we go. So we're going to do another one of those rotation problems where we're going to take a two-dimensional shape, in this case a rectangle, and rotate it around a line, and it's going to create a three-dimensional object. Now, we are going to rotate around the line x equals -1. Well, if here's our x-axis, then here's x equals -1, and I need the line x equals -1. So I need to create a vertical line that goes through that point. So I'm going to wrap this rectangle around. Okay, so it's going to get wrapped around and then it'll wrap around. So you can see we're kind of going to be making a cylinder here. Now, I need to draw the mirror image across this line, but notice there is this gap. So I need to repeat the gap over here on the left side, and then I can draw my rectangle. Well, my rectangle is 5 by 7 here. So after my one gap, I need another 2, 3, 4, 5 by 7 rectangle. So here's my mirror image, my reflected image over there. And now I need to think about what's this thing going to look like as it rotates. Well, this point in the upper left-hand corner of the original rectangle will end up being this point in the upper right-hand corner. And this point in the upper right-hand corner will end up being the point in the upper left-hand corner of the mirror image. So we kind of have two circles going on here. We have this kind of inner circle and we have this outer circle. And we're going to see the same thing happen once again down here in the bottom. So you can kind of imagine here we're creating like a toilet paper roll, right? Now, the question is, calculate the surface area of this particular shape. Okay, we've done this problem before with volume, but not with surface area. So again, we need to consider a surface area, the sum of all of the surfaces we could touch. All right, so I'm going to start with the top. Okay, can I touch the entire top circle of the toilet paper roll? And the answer would be no. I can't touch the whole thing because there is literally a hole missing. Okay, so I can touch everything I'm shading green here. I could touch all of this, but I can't touch where the hole in the toilet paper roll is. So if I were to draw a two-dimensional version of what's really going on the top here, I really have a circle with a circle hole in it. Okay, something like that. Now, what is the radius of my hole here? Well, that would just be my gap that I originally had, which was 1. And what's the radius of the overall big circle? Well, I'd have to include my gap of 1 plus the extra 5 that I had going on here. So altogether, it's 6. So I might call big R, the big radius, 6, the little radius, little r, 1. And so I want to take the area of the big circle minus the area of the small circle. So I'm going to take pi big R squared minus pi times little r squared. So I'll have 6 squared and 1 squared. So really 36 pi minus 1 pi is 35 pi. Now 35 pi represents the top of this shape. Will I see 35 pi anywhere else in this same exact shape? Sure, on the bottom. So I'm going to start keeping a list of all of my sides here. So the top is 35 pi. The bottom is 35 pi. Okay, so it takes care of top, takes care of bottom. Now, can I touch anything else in between the top and the bottom? And yes, I can touch the outside of this cylinder, right? So the outside, let me erase this, get some space in here. I can touch the outside of this, and it is really lateral area. Now, the formula for lateral area of a cylinder was pi times diameter times the height. Now, what is the diameter all the way across my toilet paper roll? Well, that would be my radius earlier, which was 6, and double it, which would be 12. Now, you might ask, what about the hole? Well, the hole doesn't matter on the outside, right? Because I can touch everything on the outside, regardless of how big that hole is on the inside. And the height of my toilet paper roll is my 7 here. So 12 times 7 makes 84 pi. So the outside is 84 pi. Now, are there any other surfaces that I could touch of my toilet paper roll? And at first glance, you might think and go, no, there's nothing else we can touch. But we can. We can touch one more surface. We can touch the inside part of the toilet paper roll, right? Where the cardboard tube is. We could put our finger inside the hole, and we could touch this hole inside. So there's really an inner lateral area. Now, can we touch the top and bottom of that hole in there? No, because that's where literally there is no area. But we may touch the lateral area of that inner cylinder. So then again, we'll have pi times d times h. So now what's the diameter of all across this hole? Well, now it's 2 because the radius was 1 previously. So all the way across that hole is 2. The height is still 7. So there's an additional 14 pi that we can touch and we need to add to this. So now how many pi do we have altogether here? Well, 35 and 35 make 70 pi, and 84 and 14 make 98 pi. So add those together and we'll get 168 pi units squared of surface area. Now, if you wanted to figure out what that is as a decimal, you certainly could, but I would personally just leave it in terms of pi. So we have the top and bottom circles that had holes in them, which we accounted for, 35 pi each. The outside lateral area, which had no influence on whether there was a hole inside of it or not, was 84 pi. And the cardboard tube in the middle that we can touch is an additional 14 pi. So that is all for the last video of this chapter.